All right. So again, if we're working under constant volume, then delta U is going to tell us the total energy change. In other words, the net energy change for the particular process. But under constant pressure, then we have to worry about the surroundings, because if the system expands, it's doing work against the surroundings. If the system contracts, the surroundings is doing work. And that's not factored in unless we also get the pressure volume states. And so we use enthalpy instead, because enthalpy is going to be the total energy, plus the pressure volume initial. And this will tell us how the energy is going to change with work P, delta V work, being done with the surroundings. So for us, delta U under constant pressure is not useful, but delta H is, because delta H is going to tell us the net energy output or the net energy input that's going to be required in the particular system. And so let's just do some comparisons so we can see how. And so this is just putting applications to the exothermic energy diagrams and endothermic energy diagrams that we did the other day. So we'll look at a variety of reactions there. Let me see. Well, this is loading. We have two ways of doing particular chemical reactions. That we focus on, and those two ways are we're going to do it under constant volume or we're going to do it under constant pressure. Sometimes we do it under one way, but we want the energy information for the other way, so we have to make comparisons. Oops, this is chapter 8. We have to make comparisons between what if we did it, so we might have data for constant volume energy, but we might think, what if we did it under constant pressure? How would that energy differ? Or we might have data at constant pressure, and we think, what if we did it at constant volume? And so things like this, 37, a bomb calorimeter experiment is performed. Did I do this last time? I don't think so. With xylose. Xylose is organic C5H10O5. It's an organic alcohol. It's combustible, so they burn it. They burn it in the bomb. So this is done under constant volume. But one of the questions that might come up is, well, what if we didn't burn it in the bomb? If we didn't burn it in the bomb, then would we get more or less heat from this particular reaction? And so, looking at xylose, what we're going to get is, we get the amount of heat, and Q sub V, delta U is equal to the amount times Q sub V, right? So delta U itself is just equal to Q sub V divided by the amount. And so we can get the heat, in joules or kilojoules here, divided by the amount, if we're having grams. So we get kilojoules per gram or kilojoules per mole if we convert the grams to moles. And so what is the heat of combustion of xylose in kilojoules per mole? Well, this is the heat of combustion. This particular heat of combustion is going to be delta U or delta H. Well, normally when they talk about heat of reaction, they're talking about delta H, heat of reaction. If they ask you how much energy is going to be output from this, then yeah. But if they're talking about heat of combustion, well, heat of combustion is normally, delta H. Delta H is normally under conditions of constant pressure, under conditions of constant volume, right? And so they're giving us data to figure out what delta U is, but they're asking us what delta H is. Well, B, write the chemical equation for the complete combustion of xylose and represent the value of delta H in this equation. Assume for this reaction that delta U is approximately equal to delta H. So in this particular reaction, let's see, are delta U and delta H the same thing? When are delta U and delta H the same thing? At constant volume. Well, it's not just constant volume, it's simultaneously constant volume and constant pressure. There's no change. Well, let's take a look at this one, C5H10O5. So we have C5H10O5 solid. And then we're going to burn this to form CO2 gas, to a liquid. So we need to balance this. So we need 5 carbon, 5 water, do it. This is 10, 15 oxygens. We have 5 here, so we just need 5 here. One of the things the book does is, if the moles of gas stay the same on both sides, so we have 5 moles of gas here, 5 moles of gas here, then they assume the volume change is negligible. And is that accurate? No, it's not totally accurate, but is it a good approximation? And yes, it is a good approximation because gases, if you compare the volume of a gas versus the volume of a solid or liquid, volume of the gas is usually 1,000 times more, than like 3 orders of magnitude greater than the volume of solids and liquids. So, we're typically looking at milliliters, but here we're looking at a lot of liters, thousands of milliliters. Well, anyway, going back to this, well, how do we know? Well, if we do this in a bomb, obviously the volume is not going to change, because it's a bomb. But what we have to do is we have to imagine if we did this under constant pressure, would the volume have changed? And so what we're going to do is we're going to switch from being at constant volume and imagine that we're going to burn this outside in the open lab under constant pressure and then see, do we get simultaneously constant volume and constant pressure? And so here, okay, so we switch our thinking. You have to do this, you flip-flop mentally from constant volume conditions to constant pressure. And so you can flip from the constant volume universe to the constant pressure universe and back and forth. Okay? And then see how things change. And so switch to constant pressure. And so if we're a constant pressure, this is what we're going to do. We're going to figure out the V initial. This is V initial. We're going to figure out the V final. And so let's figure out V initial first. We're going to assume we'll just have 1 mole of this, 5 moles of that. And so 1 mole of xylose. Well, the first thing we need to do is figure out how many grams that is. So we've got 5 carbons. So that's 5 times 1201, which is going to be 6005. And then 10 hydrogens. I'm going to go 108 because I want some more sig figs here. So this is going to be 10.08. And then I got 5 oxygens at 1600. So that's 50 plus 30 is 80. So this gives me 150.13. So I have 150.13 grams per mole of xylose. And then we're missing something. We're missing the density. We can guesstimate the density. What do you guesstimate xylose? Is it solid, organic? Do you think it'd sink in water or do you think it'd float on water? This is what you do sometimes when you don't have data. You just estimate it, so you can come up with some kind of ballpark answer. And so what would you guesstimate the density? Would you guesstimate that this organic solid alcohol is more dense than aluminum? what's the density of aluminum around? Maybe 2.7 grams per cubic centimeter. Would you guess that it's more dense than water? You know, what are most solids? You know, most of these organic solids are around 2 grams, right? Or maybe twice as dense as water. They'll sink in water. And so we could do that, but we don't have to do that because we can just look it up. And so let's look up the density of xylose. That's why we want certain numbers memorized in our head. That way we can guesstimate certain things, you know, like the wavelength of green. We can guesstimate that if we have certain numbers memorized. Right? And or, you know, the wavelength of ultraviolet or the wavelength of infrared. The people who don't have any numbers memorized can't do that, and they're, you know, that's no better. You know, if they're scientists, it's no better than somebody who knows nothing, because anybody can look something up. You don't need any kind of degree to do that, do you? No. No. In fact, well, anyway, it's 1.52 grams per cubic centimeter. So a cubic centimeter is a milliliter, so we'll go 1.52 grams per milliliter. And we're going to convert this into liters because we just have liters left, liters on the right, so liters, 1,000 milliliters. So what is the volume of the xylose here?
Does it matter that they gave you a gram of xylose?
Does it matter? Yes, it does. But you know, this is what we're doing here. I'm not answering this question here because they give us grams of xylose. So what we could do is we could just use this many grams of xylose and then figure out, you know, how many moles of O2 that corresponds to, how many moles of everything else. But what I'm gonna do is I'm skipping the stoichiometry of this, so I don't have to do that. Because, you know, what we do with this information is eventually, this is Q. We're gonna get Q from this. And delta U is going to be, well, delta U is just equal to QB divided by the amount. And so we do the amount in moles. And so now we get delta U in terms of kilojoules per mole of xylose. Well, if we have delta U kilojoules per mole of xylose, then let's just keep life simple and just do everything by the mole basis afterwards. Because they're asking for delta H. You know, delta H is going to be in kilojoules per mole, right? And so the heat of combustion of xylose in kilojoules per mole, I might as well just, if they ask me what QP is, you know, they give us QV, they ask me what QP is, then yeah, I want to do it only for this amount because I'm not burning a mole of this. I'm only burning a tiny fraction of a mole. Okay. And so the reason I do it like this, you could do it either way. You know, we could do 1.83 and figure out how much work was done there. But then after we do that, we have to normalize it per mole basis anyway. Well, what was the volume of this? All I'm doing here is I'm not answering this question. I'm just trying to see, is delta U and delta H the same thing? You know, this is just applying the conceptual stuff we did the other day. And so what's the volume of this here? Let me bring in my calculator. Oh, there's a calculator here. Well, anyway, we'll just continue. This is going to be 5 times 24.45 liters of volume, and that's going to be V initial. And then over here, we have 5 moles of CO2, so that's going to be 5 times 24.5 liters per mole. Maybe I'm running out of room, so I'll just skip the mole part. 5 moles of gas, 24.45 liters per mole. We're just assuming it's at standard, our standard, or regular or normal conditions. And then 5 moles of water. 5 moles of H2O, liquid, this is. Then that's going to be times 18.02 grams per mole. And then this times 1 milliliter per 1.00 grams. And then we'll just convert it to liters, liter per 1,000 milliliters. All right, and then once you do this calculation, compare the two. Compare. And then see, you justify if the assumption was okay or not. Okay. All right. We'll take a look at one where there is more significant change. Here, was the change insignificant or was the change significant? So go ahead and calculate it. Let's see. When there is a change in the moles of gas, the volume change will be much more significant. So let's take a look at something like naphthalene, number 41 here. Number 41, naphthalene is C10H8. And then this is also a solid. And we'll just combust this with O2 gas to form CO2 gas plus H2O liquid here. And balance this, we need 10 CO2s, 4 water, and then this gives us 24, we'll need 12 O2s. Here we definitely have a significant change in volume, right? And so here we're saying we're going from 12 moles of gas. You'll see that the solids, when you do this calculation, you'll see that the solids and liquids, the volume doesn't really change much because the volume is quite small. But here the volume is going to be significant because we're losing 2 moles of gas. 2 moles of gas is, that's about 50 liters of gas we're losing. So the volume change here is significant. Therefore, delta U and delta H are not going to be the same here. Delta U and delta H will not be the same. And so this is burned in a bomb calorimeter. So in a bomb calorimeter, what are we getting? In a bomb calorimeter, we're getting delta U. And so what are they asking for, however? They're asking for, what is the heat capacity of the bomb calorimeter? The heat of combustion. They give us the heat of combustion is minus 5156 kilojoules per mole. So we're going to do a little bit different. Approach to this problem. And so we see that the delta H for this particular reaction is minus 5156 kilojoules. And now, it's kilojoules per 1 mole of naphthalene, kilojoules per 12 moles of O2, kilojoules per 10 moles of CO2, kilojoules per 4 moles of water formed. And so this kilojoules doesn't have per mole. This kilojoules is related to each of these in the balanced chemical equation. And that whole reaction has to go as written in order to generate that much heat. And so what we're going to do is, okay, if that's our delta H, then what is our delta U? Our delta U is going to be different. And so let's do this as a separate problem. This is not going to be number 41. This is going to be something else. And so doing this as a separate problem, we got to figure out, well, delta U, what is delta U? Well, if we want to figure out what delta U is, then delta U is just equal to delta H minus the work. Or is that right? No, delta H is equal to delta U minus the work, right? And so delta U will be delta H plus the work. Involved. And so we have delta H, that's easy, because delta H is minus 5156 kilojoules for the reaction as written here. And so the only thing we have to do is figure out how much work is done. Well, the work is, this actual reaction was carried out in a bomb, and we didn't have a mole. We didn't burn a full mole of this. But what we're going to do is we're going to imagine that we're carrying this out under constant pressure, and we're going to burn a full mole of this. Because why a full mole? of naphthalene because I already have the stoichiometry. I don't have to do a stoichiometry calculation. Let's say if I burn how many grams. If I burn 1.620 grams, then I have to figure out how many moles of naphthalene and then how many moles of O2, and then, I don't want to do all that, because then once I figure out how many grams, then I figure out the volume of this, I figure out the volume of this, figure out the volume of that, right? But we'll just go ahead and normalize it because we got the kilojoules per mole here. This is kilojoules per mole of naphthalene burned, and so we know it. And so the work is, well, if a mole of naphthalene burned, what is the work involved? Well, the work is just P delta V work, so it's minus P delta V. And so there are two ways to do it. Petrucci assumes this. Petrucci assumes, and you can see in the calculation that was set up earlier, that Petrucci assumes that solids and liquids volume change is negligible, so ignore those. Only worry about gas volume changes. Well, we don't have to do that. We can factor in all those if we have the density. Unfortunately, we don't have the density of naphthalene, but we have that available, so we just go ahead and use it. And so we have 1 mole of naphthalene. Naphthalene is going to be 120.1. Plus 808. 28. And so we have 1 mole of naphthalene.